Everybody, my name is Gabby. I'm here with Momo, Wing, and Rebecca. Today we're doing a topic called rational functions. And our experiment that we're going to do today is called light intensity as a function of distance. Now, let's do our experiment!
Explanation on our chosen topic. So in mathematics, rational function can be any function which is defined in a rational fraction. For example, a function is called a rational function when it's in this form. Where P and Q are the polynomials in X, and Q is not the zeros of the polynomial, where it is actually the asymptotes, the vertical asymptote.
A little backstory about our experiment. It's to measure the intensity of brightness of light from an amount of distance. So basically our experiment, it has an inverse square relationship. And for example, the further the light source is from the screen, the further the distance, the weaker the light intensity. And the closer it is, the brighter and more powerful the light intensity. And that's basically our experiment for today.
Alright, so now that you understand the gist of this experiment, we shall do it together. By the end of this video, you understand to relate this experiment with rational functions. Alright.
So basically, now we actually did our table, we plotted our graph, but we want to show you guys how we actually collected these values, right? And we're using a flashlight as a source of light. I'm gonna point in this case. So when I point the flashlight at the board here, now as I'm standing further away from the board, you guys can see that the light intensity is really low. And this is what our table here shows. When the distance is closer to the board, the light intensity is higher. When the distance is further, the light intensity is lower. And now we're gonna show you guys by taking measurements, just like the one in our table here. Okay, so Gabe's gonna explain.
Okay, so based on the measurements I've taken, we're going in intervals of 2, 4, 6, 8. Now first, we'll be starting with 2 centimeters. And please take note of the light intensity as I move backwards. This is 2 centimeters. This is 4 centimeters. This is 6 centimeters. And this is 8 centimeters. So could you see how it radiates outwards as I move backwards? So when I go closer, the circumference is smaller, the area is smaller, the area of which the light covers is smaller. But when I move backwards and the distance increases, the area becomes larger.
Function. So we're gonna plot our points.
When r squared has a value of 4, our intensity will be 0.25.
And then 16, 0.0625, 36, 0.028, and 64 is
0.016.
So this is not really perfect because we're not drawing it on a graph paper, but this is just show you guys that it has asymptotes. And if it has a vertical asymptote and a horizontal asymptote, that shows that this graph is a rational function. So in this case, our vertical asymptote will be the y-axis. Vertical asymptote, y-axis. So x equals 0. Horizontal asymptote will be the x-axis, which is y equal to 0. And then our domain and range here will be, the domain will be the x, from 0 to infinity. Our range will be the same.
As you know, the function of intensity is that the distance and intensity is inversely proportional. And here, now we're going to move on to the relationship between distance and area, where we're going to find out the relationship where it is directly proportional by taking measurements on the board by calculating the diameter from the light source and using this formula to get the value of the area.
2 centimeters away from the board, and we're gonna measure the diameter. 10.5. So the area is gonna be 25 to
86.5.
6.5. And the second one, 4 centimeters away. Okay, now
Yeah.
14.3.
Hundred and 58.
That's it.
Around 20 centimeters.
Around approximately 20 centimeters. Okay, so 20 centimeter, that's pi 20, say 20 over 2 square.
Which is 314.2.
Okay. Then 8 centimeters away from the light source. Okay.
Twenty 21 centimeters. Approximately 21 centimeters.
So a pi 21 square.
346.4.
You know, we should have turned.
Okay, now we're graphing the area against distance graph, and we'll be using this table, which contains our data, to plot this graph. Okay, so now I'll be drawing the x-axis. So we'll have 2, 4, 6, 8. And then for the values on the y-axis, we'll have 86.5, 158, 314.2, and 346.2. And now we running the graph. can see here, this is actually a linear graph because when x increases, y increases. So from this, we can conclude that these two components, they're directly proportional to each other. This is why we can derive a linear graph. Okay, so now we're going to find and determine what is the equation of this graph. So using the graphing calculator, you're going to get a linear regression in the form of y equals to mx plus c. So the value of a is going to be 46.765. And this a is actually our m, which is the gradient. B, which is supposedly our c, is negative 7.6. And this is our y-intercept. But then since our y values cannot be below 0, so we won't graph the value of negative 7.6 onto our graph.